Okay, I'm going to record this for a second time because I got done recording it the first time and everything got completely wiped from my phone for no reason whatsoever. So we're going to take a second shot, or I'm going to take a second shot. For you guys, it's the first. I'm going to take a second shot at talking about masses on springs. So this is very similar to pendulums with an object swinging on a string, except now we have a mass on a spring. Similar phenomenon happens with a mass on a spring. Originally, no energy is stored when the system is at equilibrium. This means when the spring is not stretched or compressed. And we're talking mostly about a horizontal spring mass system. So you've got your mass resting on, let's say, a surface and a horizontal spring attached to that and a wall. So when the system is at equilibrium, meaning the spring is not stretched or compressed, no energy is stored. If a person comes along and does some work on that system, in other words, they take, let's say they take the mass and they pull the mass and spring out so it stretches out the spring, they're doing work because they're applying a force over displacement, and since work changes the energy, we can ask, well, what type of energy changed? Since they're elongating or stretching a spring, they are storing elastic potential energy in the system. Elastic potential energy is increased. Okay? They could do the same thing by compressing it, by pushing the spring in. That would store the exact same amount of energy for the exact same amount of stretching. When you release it, that elastic potential energy is going to decrease because what's the spring going to do? It wants to go back to equilibrium, so it will go back towards not being stretched at all. But that means the elastic potential energy is going to decrease. Where does that energy go? It must be converted into kinetic energy. So we have this little system here where we have a spring, an object on a spring. You can see a horizontal spring. Here's our object, and this says 0, so that's at equilibrium. It's not stretched or compressed. If we were to pull it out to X max, we'd be storing elastic potential energy inside the system, but when we release it from here, there's not yet any kinetic energy. When we release it and it goes back towards the middle, the elastic potential energy should decrease because as the stretching goes down, that energy's got to go somewhere, turns into kinetic energy, so that when it gets back to equilibrium, there's now no elastic potential energy, but there is a lot of kinetic energy. So this object's not just going to stop, now it's all got all this energy. It's going to compress the spring, it's going to keep going. And as it compresses the spring, what goes down? The kinetic energy, because as we compress the spring, the potential energy of the spring has to go up. So as the kinetic energy goes down, the elastic potential energy goes up until we hit X min. This is the farthest distance of compression that we get with the spring. And since it's as compressed as it's going to get, this is also where the kinetic energy is 0. And then the same thing happens. The spring pushes the box back. As it pushes the box back, we have gaining kinetic energy. We're losing elastic potential energy to the middle. And if there are no other forces, we get this object moving back and forth, trading kinetic energy for elastic potential energy forever, essentially. So in this example, let's say that we have a horizontal spring of spring constant 200 newtons per meter, and it's attached to a 10 kilogram box on a frictionless surface, and that's key here. Frictionless means we're not going to lose any energy to internal energy, and that most importantly means that this object won't ever stop, okay? It's going to go for forever. Again, in real life, this doesn't really happen, but we're treating ideal cases for right now, just to start. So on a frictionless surface, it will go back and forth for forever. There's also once you stretch the spring out and let it go, there's no work being done by outside forces. There's now no more applied force once you let it go. There's no tension. Okay, there's a spring force, but that's accounted for by the elastic potential energy. And there is a normal force, but once again, it's perpendicular to the displacement and does no work. So, first question, is the system's mechanical energy being conserved? Why or why not? And the answer is yes, because there are no outside forces doing any work, and because this is a frictionless surface, so therefore there's no internal energy. The only types of energy that are present are kinetic and elastic potential energy. What we want to do is calculate the kinetic and potential energy at each point of the box's motion. So first thing we did is we calculated the elastic potential energy at X max. At X max, there is elastic potential energy, but no kinetic energy. So we use our equation, 1/2 kx squared. We know that the spring constant is 200 newtons per meter. and the stretch is 0.04. Therefore, when we calculate that out, 1/2 times 200 times 0.4 times 0.4. We get 16 joules of kinetic energy. Since there's no kinetic energy, that's 0. Therefore, the total energy in the system is just the elastic potential energy, 16 joules. Now, at equilibrium, it's a different story. There's now no longer any stretching or compressing of the spring, so the elastic potential energy is simply 0. So ET equals PES plus KE. There is no elastic potential energy of the spring. Therefore, the kinetic energy is simply 16 joules. We could go and figure out the speed, but that's not what the question asks for. And then finally, at X min, this has got to be the same as X max. There's no kinetic energy here. This is the turning point. So therefore, the object must be stopped, not moving. And if it's not moving, then that means that since there's no kinetic energy, all of that energy has to be elastic potential energy. So another 16 joules of elastic potential energy, and since the spring constant hasn't changed, that means it's compressed exactly as much as it's stretched. And this will continue to oscillate back and forth for forever, transferring kinetic energy to elastic potential energy and back. Of course, in the middle, okay, we have situations where, between X min and 0 and between 0 and X max, we have situations where we're not at a maximum, where that has both elastic and kinetic elastic potential energy and kinetic energy, but we didn't feel like finding those. We just didn't bother finding those, okay? And it's not that the elastic potential energy and the kinetic energy in the middle are equal to each other. They are equal at one point, but they're not always going to be equal. If you just move this in a tiny, tiny little bit, you're going to have a tiny amount of kinetic energy and still pretty much all of your elastic potential energy. Don't go thinking that PE and KE, when they're both present, are the same. They're not. So that is conservation of energy for pendulums and springs. I want to talk very briefly about your homework that will be due on Monday evening. When you get back, you can have the weekend to do it. This is the pendulum and springs homework in your packet. The front of it actually has nothing to do with pendulums and springs. It is simply a guy who is skydiving, and the first question is find his gravitational potential energy. If he's skydiving and he's just jumping out of the plane there, then think about what that means about the types of energy he would have. He's just jumping, or a better word might be he's just falling from rest out of that plane. So think about the types of energy that you would have and how that would affect the total energy. Then for 2, A, B, C, D, E, and F, as he falls, your job is to calculate the gravitational potential energy and kinetic energy as he goes down. Now use some common sense with this. There should be a pretty noticeable pattern to follow. I do still want to see the work for this. There should be a pretty noticeable pattern in terms of how his kinetic and gravitational potential energy change as he continues to fall. And then for G, we have a little bit more of a reality-based question. In reality, he's going to maximize his speed at terminal velocity. This is the fastest. Terminal velocity just means the fastest that something can fall. It's different for every object, and it's due to air resistance. If terminal velocity, and it gives you the speed for terminal velocity, we want to know how much internal energy has been generated when the skydiver has fallen a certain amount. Okay, so you'll have to do some more calculations there, a little bit more involved. On the back, I'm not going to say much. The calculation stuff is usually pretty easy for people. I will tell you, read directions very carefully on the back. Okay. Reading directions on the back is crucial. Usually when people mess up the back, it's because they don't read the directions. So please, please, please read the directions carefully. I'm not too concerned with the calculational parts of that homework. As always, if there's any questions, you can ask me on Remind or over email. Okay? There's one other thing I wanted to tell you about, because I'm bored, cooped up here in the apartment, just like you guys at your houses. Yesterday, what I did was I fashioned a pendulum myself out of some string and my lunch pail, and I used it to measure actually the acceleration due to gravity. The next nice day, I can't really do it today because it's a little too windy, but the next nice day, what I'm going to do is I'm going to get my roommate's help. We're going to go outside. I'm going to film this, how to do this. You guys could even try this at home if you wanted to. And you'll see how you can use a very simple equation. I never really understood why we don't talk about it in this class. but it's just not in the curriculum. We're going to use a really simple equation to figure out, to predict or measure the acceleration due to gravity outside my apartment and compare it to the accepted value, as you guys know, of 9.81 meters per second squared. Yesterday, when my roommate and I did this, we got a percent error of about 3%. This experiment works really, really well. And so therefore, it's something you can do at home, and I think it'd be kind of fun for you guys to try. Just to do something sort of interesting and maybe, alleviate the boredom for a little bit. Okay? So look for that. As always, if you have any questions or you need anything at all, feel free to, don't hesitate to contact me on Remind or through email. And hope everyone has a nice weekend and you can find some good stuff to do. And like I said, that spring and pendulum homework I'll look for on Monday. And, if you need anything else, let me know. Have a nice weekend. Bye-bye.